We still have this down and I got more paper.
Oh, good. So the shrinking is good though?
I've been only like 2 episodes in, so I feel like I can speak for the whole series, but so far
Promising stuff.
Yeah.
Okay.
It's
Harrison Ford and Jason Segel, right?
yes.
Yeah, I mean, I like both of them, so.
Yeah, it's really funny to see Harrison Ford like a different character.
Not in the Harrison Ford role.
Yeah.
All right, let's do a little review here on epoxides and reopening reactions and such.
That's what they should do. This is what they should do.
The first step of that, the Bronco step,
Yeah.
actually makes an epoxide, right? So you start by making an epoxide.
Okay.
And then you follow it up with the strong nucleophile, which is what we did in the second half last week, or last lecture, right?
Yeah.
So the first step looks like this.
Okay, I got that.
So then if you give it a strong, remember a Grignard reagent, it's gonna be a strong nucleophile. So in this case, we've got a methyl carbanion, basically. So anytime you see a Grignard reagent with that magnesium bromide attached, you can think of it like this, or whatever is attached to the magnesium is going to have a negative charge. So that's our strong nucleophile. So where is the nucleophile going to be attracted on our epoxide?
Tertiary bond is stronger one, so it's gonna attack the other side.
So tertiary bonds, tertiary carbons here. So what do you think of that?
Oh.
It's the right way to be thinking about it, but not tertiary. You got a primary carbon, secondary.
I was like, there's 3 1.
Okay, this bond is the weaker bond.
Okay. So it goes to the.
So it goes to the north side.
That's plus,
And it's still plus N. This is not a serial, or a serial center anymore, or it never was really,
Yeah.
because it has 2 hydrogens attached, so we can just turn that wedge into a regular bond, but it's worth showing it as the wedge, just so that you can remember that your other one is coming from the opposite side.
Yeah.
Give you another couple minutes on the rest of them, we revisit the reopening reactions.
That's it. That's what the HG. That's it. But does everyone have their part? Yeah, that's. No one here is going on.
Good catch. So it's not gonna add an OH group or substituted carbon, it's gonna add a methoxy. And ether. So our intermediate after step one, so initially when we just add the mercury, right? Mercury makes a three-sided ring, just like the epoxide. Then the methoxy is going to come in and attach opposite of the mercury or substituted side. And we still have a stereo center, right? Because the second carbon here is still gonna have 4 unique things attached to it. So we get a plus EN. And then the second set is just finishing up across mercuration, right? That's the demercuration set.
Yeah.
So the NADH4 in this case is just gonna get rid of the mercury. So our final product is R plus S, or you could draw one and write plus EN. Since we've been doing it more that way, it probably makes more sense. Keep it consistent. C is pretty straightforward since we did A. If we wanted to review that mechanism, since we didn't review that mechanism before the midterm, you can remember what that Rocco looks like. So our peroxy acids look like a regular acid group, but with an extra oxygen shoehorned in there. So what the reaction does is it takes one of these extra oxygens and adds it here.
Yeah.
The way it does that, lone pair grabs the hydrogen. And then you can also draw that one going over. And some textbooks will actually just show the pi bond reaching over and grabbing the hydrogen.
Okay.
This is a little bit more reasonable based on where all the electrons are. It has to be the lone pair that's pointed towards the hydrogen.
Yeah.
So it makes a little bit more sense to show it like this. That's going to form the carbonyl bond on that side. electrons that are part of the oxygen hydrogen bonds, form one of the carbon oxygen bonds to the peroxide, and pi bond to this side, form the other carbon oxygen bond. And so we have quite an elaborate little ballroom dance going on of electrons, which is good practice for what we're going to be dealing with today. So once we get there, that just gets us to this spot, and then we have speed.
Wait, why did it change to be number dollars?
I probably should have written this one on the bottom side as well, because remember, the bonds that are coming out of the board should be away from the two bonds that are in plane of the board. Because that's a little bit closer to how it really is. Because remember that, so then there's that other hydrogen is this way. And remember, our bond into the board and out of the board should be general directions each other. So this is a little bit more accurate. And then our methyl ion, methylthiolate, I think, is going to come in here to the more substituted carbon.
Plus here.
Plus, yeah, thank you.
Does it matter which one?
No, the sulfur is not chiral because it has two lone pairs, just like an oxygen. So it's got two identical substituents on it. So it's not a stereocenter. I was going to make a joke about sodium, but no. So just sodium does the same thing as we showed it once, but we usually use this version. Does the same thing. It irreversibly deprotonates alcohol. No. So this is an alcohol reaction. So all it does is the alcohol is acidic. So when it's like this, it's easy to say, okay, the hydride is going to grab the alcohol and the hydrogen gas. Without the hydride, it still does the same thing, but it's because the sodium is so good at giving away its electrons, it will give an electron to a sodium or to a hydrogen anyway. That's
It protonates it or it deprotonates?
the net result is this hydrogen turns into hydrogen gas, and the alcohol gets deprotonated.
Got it.
So initial product would just be plus sodium ions, sodium ions.
Yes.
Right, and then if we're really being careful, we could write it like this, as a way to just say that it removes itself from the system. So it's not part of the equilibrium reaction anymore. Which that's really the important part about that is that that's what keeps it from being a reversible deprotonation, is the fact that we're removing the hydrogen system. So you can't just put the hydrogen back on. It's not an equilibrium reaction. So then we bring in the epoxide. We always do the ring opening, the nucleophile effects or substituted carbon
For the epoxy.
when you have the epoxide, yeah. And actually, all of these three-sided rings we see, like the mercury one or like the bromine one, they all have the same logic. It's all your nucleophile that comes in to do that ring opening reaction always goes to the more substituted side because that's what the weaker bond is. Very good.
Yeah, why did the oxygen with the negative disappear?
Because it shouldn't have. Thank you.
I was really confused.
My pentagon was better than first time, but this has the actual right atoms. So So with these ring opening reactions, the only thing to really be paying attention to is what's my nucleophile. And remember, the nucleophile always goes to the more substituted side. Other than that, they're all the same. All right. Let's do something new. We've just been racking up new mechanisms and functional groups for the last 5 weeks or so. Let's do a functional group that's based entirely on the orbitals. We're going to talk about dienes together today. So dienes, it's just an alkene when you got two of them. Diene. And we name them like that too. We just say diene at the end. So if we had this molecule, our longest continuous carbon chain is still 4, right? So it's still going to be bute. And when we're naming these, we just leave the A on from the alkene. So it's not butane. We drop the NE and then we say diene. So butadiene. Two alkenes with the same molecule. Just like any other time we've got a functional group that could be more than one spot, we do need to specify where they are. We have to specify where both of them are. So we would call this one carbon 1, that's carbon 3, it'd be 1,3 butadiene. as opposed to this molecule. That's going to be pentadiene. And no matter which way you count it, it's 1, 4. So it's 1, 4 pentadiene. Right, so same rules as we've had before, we've just added this diene piece. So there's 3 classes of these. We're gonna spend most of our time. So the thing about the isolated dienes, when we've got 2 alkenes, but they're on opposite ends from each other, and they have at least 1 sp3 carbon between them, those pi bonds can't really interact if there's an sp3 carbon in the middle, right? So one of our first rules of resonance was you can't resonate electrons through an sp3 carbon. An sp3 carbon is tetrahedral and already has bonds, sigma bonds. So you can't move any electrons to or from an sp3 carbon when we do resonance structures. Does that sound familiar? So basically an isolated diene is going to behave just like an alkene. There's just 2 of them. All of our same alkene reactions apply. It's an isolated diene.
And isolated is when there's an what S?
When there's no resonance between them, or if there's an sp3 carbon in between them, you can't have any resonance structures. The other type that doesn't, so isolated dienes, they show up fairly frequently, but we just treat them like alkenes. They're not a separate function. Even though we would name them as a diene, they're going to behave identically to alkenes. You just need 2 equivalents of whatever reactants you're using. Because there's no way to pick one of these to have a reactant not react to the other one. Accumulated dienes, which are also called allenes, they're a little bit different, but they still don't have any resonance. Because if you look at the way that the electrons have to be, in order to put 2 pi bonds on the same carbon, they have to be perpendicular to each other. If they're perpendicular to each other, they can't have resonance. So these accumulated dienes or allenes, they kind of do their own thing, and they're really actually pretty uncommon. We don't see accumulated allenes basically ever. They do exist. If you work really hard, you could make them, but they don't really have any commercial application that I'm aware of, and they're unstable and hard to make. So they're more of a novelty than anything else, as far as I'm aware. I'm sure that there's some research going on that might change all of that, but at this point, you don't need to worry about allenes too much once you know that they exist.
And there's still no resonance.
Then there's still no resonance. What makes dienes different than just regular alkenes are the conjugated dienes. So conjugated dienes, when you have your pi bonds 1 carbon apart, so that their orbitals can all line up, we get lots of resonance there, and that helps stabilize things. So let's do practice, just classifying them. For each of these compounds, figure out whether or not the carbon-carbon pi bond is accumulated, conjugated, or isolated. It's not necessarily with other carbon-carbon pi bonds, just with other pi bonds in general.
And I can have another.
So for the conjugated acid. I believe you pronounce it conjugated, even though the enzyme breaks it down, the citric acid cycle, it's a convertase. I think it's activating, it's not con. I couldn't say it the other way.
There's two different conjugated.
This whole thing, this whole area all has resonance with each other. So you could say that those two bonds are conjugated, but those two are conjugated as well. So this whole area is going to have pi electrons that are all facing the same way. So you actually have 3 pi bonds that are conjugated in this case. And that last is isolated. Osamine has some conjugated pi bonds.
You just, I want to you circle like. Up to the next. Five bonds.
If the problem said look, determine if each pi bond is isolated or accumulated or conjugated, then I would the color coding, this would be a different color. This one on the top right, so it's not going to state anything else. So this one's isolated. These other 3 are all conjugated. This one's really interesting. So based on the name of this, we can guess where it's found naturally. Yeah. So when they're giving things common names, they're at least courteous enough to usually give us some sort of hint, oftentimes. This one's interesting because this is one of our examples that we used for when we first looked at stereochemistry and R versus S. Because R carbone is the flavor scent of spearmint. An S carbone is the smell of caraway. Very different. Caraway's in dill pickles a lot. In bread, see caraway seeds on everything, bagels, things like this. Much more savory.
Yeah.
It's not minty at all. But oddly enough, so one of my labs when I was an undergrad, we made the racemic mixture of R carbone and S carbone, so a mixture of both of them at the same time. And for about 6 months after that, I couldn't tell the difference between caraway and spearmint. It confused my brain, so that I couldn't. It was really confusing to me. Yeah, I couldn't separate it.
So did you ever eat like peppermint ice cream and we're like, oh, it's really safe?
So peppermint is menthol. So only spearmint typically only gets used in gum, and sometimes in Thai food. But wintergreen and all those other types of mints actually mostly use menthol, which is a different compound that has the same effect on your taste buds of making it feel colder than it is. But it does not have the same molecular structure. So spearmint is a little bit spicier of a minty taste. But I did avoid spearmint gum for about a year for that experience.
That's so crazy.
And the whole lab just reeked of it for an entire 3 weeks because it was like a 3-week lab. We made it and then we had to separate the icebergs and then we had to measure. We did not taste it.
Yeah.
My professor was old school, but he wasn't that old school. All right, so how do we make a conjugated dye? So if we do a double elimination with a really strong base, we get an alkyne, right? If we use a sodium amide. If we use a strong base but not that strong, especially if it's sterically hindered, we get conjugated dye. I don't actually think it even needs to be sterically hindered, but if it's sterically hindered, you will definitely not get the alloy version, the accumulated version, because it's going to pick the least sterically hindered hydrogen to remove.
So is it always gonna be the TBO
TBO is the most common one now.
by itself?
Yeah, I think we usually just do that, use that one by itself. And we'll make a little bit of bromide, potassium bromide is our side product. Because I see. Right, and this is our sterically hindered base. That's our classic sterically hindered base.
Start. Our starting one.
Yes, we have to put the bromine there before this works. If we don't have the bromine there, so we might have the brominates do this first. So if we were trying to start just from butane, this is a good synthesis practice. If we're trying to get to this from butane, we're starting here. We can use bromine and light, do our free radical reaction. It's going to give us this R plus S. Then we can do an elimination reaction to give this. So if we did NaOET in heat to favor the elimination, we would get this, which then we can do Br2 without light, because that gives us our dibromination. And then we're going to use TPOK. So getting our halide with our halogens in the right spot is a non-trivial issue. It's something that still takes time and effort to do, but we know how to do it.
Yeah.
Which is also why, if we were doing this in a lab and we were interested in this step, and we didn't care about studying the first steps because they're already well understood, we would just buy this. This is commercially available. It's just a matter of how expensive is it versus how expensive is it to make it in-house.
Because our yield is gonna be so bad,
Going through 5 steps to get to it. And if we're using it all the time and we cared about the purity, we didn't need to want to worry about it, we'd probably just buy it. If it's something that's not commercially available, we'd have to make it in-house.
Yeah.
And that's why synthetic chemistry is still such a big deal. Seems like it's all well understood, but pharmaceutical chemistry keeps finding new molecules that seem like they'd be interesting. So synthetic chemists have to start keep finding new ways to make those molecules and make it economical. And basically if you get a degree in synthetic chemistry, you don't necessarily have to do your own research. We could get hired as essentially the in-house expert for a research group in pharmaceutical chemistry. You're just the one who makes all the stuff that they go use. Your job is just to keep them supplied with the reactants they need and find ways to do it. And you might publish some papers here and there along the way, but your primary job is supporting the rest of the group.
Yeah.
all right.
I mentioned we probably don't need to use a sterically hindered base because it turns out these conjugated dienes are way more stable than cumulated or isolated dienes. Well, I guess not way more stable, 15 kilojoules per mole, but significantly more stable. 15 kilojoules per mole. Let's see, divide that by 4, say 3.5 kcals per mole. And I guess every 3 kilojoules per mole, 5 kilojoules per mole, is a factor of 10 at room temperature. To be a factor of 10, so 10 to the 3 times, so 1,000 times more favored by equilibrium.
Okay, I remember this equation.
Yeah.
If you plug in room temperature for T, you can actually estimate what the difference is based on in K based on that. And so that's a number back from my grad school days that we used all the time. 1.5 kilojoules per mole. 1.5 kcals per mole is a factor of 10 difference. So that's about 5 kilojoules per mole is a factor of 10. So 3 factors of 10 difference.
I have a question. Can you go
Yeah.
back?
Absolutely.
So for when we drew it out, then like here, this step, we could just go from here to here. It would go from this to that to the bottom.
Right.
Make that. And then
Right.
do the step again and make that.
Correct. So if it's easy to make this, you can also just start here.
But it would be like you go from that, do the step, you get that, do the step, you get that. Okay.
Yes. If you're showing all of the steps. The reason we have it written out as a separate reaction down here is because we have a separate reaction to specifically put a bromine in the aluminum position. So if you already had an alkene. So let's say we had cyclopentene and we wanted to make it cyclopentadiene. We would want to put a bromine right there. If we could put a bromine right there, which we know how to do that with NBS light, specifically puts the bromine in the allylic position. So we don't need to add 2 bromines just to take 2 bromines off if we start with an alkene in the right spot. So we basically have 2 different pathways that converge here. Either have this pathway starts by going here and then here, or this pathway gets us here and then here.
Right. But so like then just for the top one, that's like our intermediate.
Yes.
And now that we know all these reactions and mechanisms, the tricky part is keeping them all organized and remembering them.
Yeah.
Which is why synthesis is such a big part of this part of class. It wasn't before. We needed all these reactions or else it doesn't really make any sense. All right, so conjugated dienes are more stable than isolated dienes by about 15 kilojoules per mole. So a significant amount. Why might that be? You think I already mentioned it, then you're probably right.
It has double the bonds.
It's double the bonds, but if we look at this would be if we had 2 moles of isolated dienes, or if we did this with, we could do the same reaction with this one versus
Wait, how are those more stable if they're lower on the?
lower in energy means more stable. Right? Things flow downhill.
Is it the rest?
It's the resonance. When it's isolated, you don't get any resonance stabilization. And remember, the resonance stabilization allows us to spread the electrons out more. Where the electrons can be more spread out, they're more stable. The more confined they are, the higher energy they are. Which is just good quantum mechanics review. You remember that? So sigma stands for the uncertainty. The uncertainty in the position times the uncertainty in the momentum. This is using P the way physicists use P. Must be greater than or equal to Planck's constant over 2. We never did any math with it, but that's the way of what we more commonly call Heisenberg uncertainty principle. But the Cliff Notes version, the non-mathematical version, people don't even use Cliff Notes anymore, so that even still makes sense.
Yeah, when we were kids,
People still use them. Okay, so I've got another problem here before I have to phase that one out. The AI overview version is you can't know where something is and how fast it's going at the same time. So the more you keep an electron confined into a small area, the faster it has to be moving because there's more uncertainty in its both in its location. You're decreasing this, so you have more uncertainty in its momentum. And so the more we can spread the electrons out, the more stable they are, the lower in energy they are. All right, so if we've got a conjugated diene, and for the most part, when we say dienes, we mean conjugated dienes. Most of what we're going to talk about for the rest of this chapter is all conjugated dienes. So if I just say dienes, assume it means conjugated dienes, but I will be specific about what our molecule is as much as I can. So 1,3-butadiene actually has 2 stable conformers. They have one where your 2 pi bonds are pointing in the same direction and one where they're pointing in opposite directions. This is a sigma bond. It should be able to freely rotate, right? Except for the fact that if we have resonance, we actually have orbital overlap across the sigma bond too. So what this means is we actually get what's called a hindered rotation. Where it can't freely rotate. You can rotate between we call this the S-cis. S means we're talking about the sigma bond. Okay. So the sigma bond is cis versus the sigma bond is trans. We can switch back and forth between those, but it's not easy to do. Because in order to do that,
we would have to take this piece and rotate it 180 degrees, right? Which means we're gonna get to a spot where these pi bonds are perpendicular to each other, they're no longer parallel. If they're perpendicular to each other, we can't have resonance. Just like we saw back here with the accumulated lines. These have no resonance because the pi bonds were perpendicular to each other. So in order to get from the S cis to the S trans, we actually have to break that resonance. And then we reform it once it gets to the other side. So if the conjugated dienes are 15 kilojoules per mole more stable than the isolated dienes, what's your guess for what's the activation energy to rotate from the S cis to the S trans? Make a lot of sense if it was 15 kilojoules per mole. And that is in fact what we see. Because basically it should be able to freely rotate. There's not a whole lot of sterics getting in the way, other than the fact we have to break the resonance too. Right, so the S trans is about 12 kilojoules per mole more stable than the S cis. Does that make sense? What's different about this?
Like they're not pushing on each other.
Yeah, that's sterics. You had it right.
It is hysterics.
Yeah, when we're in the S trans position, our two methyl groups are pointed in opposite directions from each other, so they're not bumping into each other. Because remember that these carbons, we're not drawing the hydrogens, but there's two hydrogens on these two that are in this plane that's drawn here, right? Because they have to be, if this carbon is sp2, it's trigonal plane, right?
But if we can't rotate this one, how do we get to the trans?
It does rotate, it just doesn't rotate. It's hindered, not prohibited. Hindered just means something's the way. So for context, again, this is not a number I would expect you to have memorized. Say it again.
Bring something to it.
We have to break the resonance right here. Well, it's happening kind of all the time, consistently, because remember that number I had memorized about for every 1.5 kilojoules per mole, it's about a factor of 10 difference in the equilibrium constant. That also applies to the rate constant, which has this form, right? And I just, from my grad school days, have a number memorized where we can say it happens reasonably fast at temperature. It's about 100 kilojoules per mole. About 25, about 25 kcals per mole, which is about 100 kilojoules per mole. We can say that reaction happens relatively quickly. We're only at 15 kilojoules per mole to do this rotation. So it's not going as fast as it could be. It's not like it's free to rotate, but we're not really holding it in place that tight.
So we don't really do anything
It just does this.
like the residues of where all the electrons are.
Exactly. So this is the equilibrium reaction where it's constantly flipping back and forth between these. It's just slowed down a little bit because of that 15 kilojoules per mole barrier.
And it's just because those electrons aren't always.
Exactly. We're almost there. Quick hard for the rest of the quarter, then we get a week off. Well, all of us have paid.
That's so funny, a week off, guys. Like a break from one of your schools. My school breaks so much. I know.
If it makes you feel any better, I'll be working that whole week too, so because I gotta get ready for next quarter.
I'll probably be sleeping in shifts here too if I can.
Yeah. I'll be around.
Me too. Hey, stop looking at me.
All right. So I just threw this one in there to see what it would look like if it wasn't conjugated.
Yeah,
If these carbons were sp3, that should be an sp or a CH3. I think I just grabbed this from Mastering Organic Chemistry. It gets a little bit more complicated because we have three things attached there. So we have a methyl rotating around, but we also have the two hydrogens. And so it gets a little bit more complex, but the biggest activation energy is only 5 kilojoules per mole.
yeah, this. What?
If it's not a diamond, if we don't have the resonance. So just to prove that it really is the resonance that's causing this barrier instead of it just being sterics.
So what are we just trying to go? What are our?
I knew I should have grabbed. Let's take a break. Let me go get models. We'll build them. We'll take we're in a good spot for a break anyway. So
I just like don't understand how the graphs are connected. Everything else. Same.
I will show you.
We'll get there.
Yes. Let's come back at 11.
Okay. What do you have to do? I'd like to grab some coffee. Huh? Thank you. It will try to still talk about that my other stuff. After. It means to look at it, it's not stuff one.
All right. Sorry, I got caught up reliving Valence's championship game. It won, but it was controversial. Yeah.
Wow.
There is, so it was very low scoring game. They're very good defense. Our team could not get our shots. So we're taking off the good shots, but they just would not go in. So at halftime, it was 2-0. It was 2 free throws. And after the third quarter, it was 2-4. Still us. Still Valence. And then scoring started, but it was paired the whole way. And so it was 6-6 with a minute left.
Okay.
And this team had beaten us 3 times already this season. But it's been getting progressively closer every time. And there was a controversial traveling call because one of the girls grabbed the ball. She slid to grab the ball as it was rolling and then stood up, which is traveling.
Okay.
You have to dribble the ball when you stand up with it, or else it's traveling. And so she got called for that right after our team did the same thing, but dribbled it standing up and didn't get called.
Okay.
So they were yelling at the ref about that. And
That's it, that's literally like the job to make that call.
right. Yeah, it was just a whole thing. And then their coach was yelling for a timeout, but the ref couldn't hear him because he was yelling at the other team's dad on the sidelines. And our team has the ball and it's just like, I didn't hear a whistle, I'm going,
Yeah.
we scored a basket, and that was when ended up being proven. So we had to explain we're explaining all that to our friends who also have kids in that league.
Yes.
Anyway. All right. Here's our models. So what this is showing, this is butadiene. It doesn't show the resonance because remember, if these are 2 pi bonds that have their p orbitals up and down overlapping, they're also overlapping this one across that signal bond. So if you rotate it, you have to break that extra resonance that you would get.
Yeah.
And then you reform it when you get to the other side.
Okay.
So that's what this is showing.
Yeah.
This one is showing this molecule. So it's just butene. So it's just no resonance whatsoever, and it's more complicated looking. Because this part that's rotating now has a methyl and two hydrogens that are all going to interact with this hydrogen or this over here. So when this rotates, it's got a more complicated shape to it because it's got three things on this carbon instead of just two. Okay, so this is just showing you that how small those numbers are.
Yeah.
For this molecule, because there's no resonance, it's still a complicated looking sine wave, but it's much smaller because our largest jump in energy is only 5.6 kilojoules per mole instead of 15. And it's just this one. So when it rotates like this, and you get this methyl passing by that carbon, that's going to be this biggest leap, is when the two carbons are eclipsed with each other. So don't get too hung up in the exact numbers. I'm just trying to show you that, yes, we can actually prove pretty well that it's the resonance that makes the difference in the rotation. All right, so quick review of molecular orbital theory. You remember these graphs? You bring two p orbitals up to each other. They form a more stable version. So the two p orbitals just look like our figure eights.
Yeah.
And just to use the same colors roughly that are here, if they look like this, when they come up next to each other, we can get those orbitals overlapping. We have the red on top and the blue on bottom. When those get close, we get a bonding orbital that looks like this. It's lower in energy than either of them separately because we get to fill valences. However, if they happen to be reversed, so one of them has blue on top and red below, when they come up to each other, they can't actually overlap because you can't get orbitals that are out of phase to overlap. So we get the opposite. We get an anti-bonding orbital. So an anti-bonding orbital just means that our phases are opposite. And so it's generally speaking, if it's symmetric, if they're both carbons, then as much as this is lower, this is higher. So to break one of these pi bonds just using light, we can do that. We just have to shine light that has a frequency that matches with this energy jump. Because as soon as we bump an electron from bonding orbital to an anti-bonding orbital, the whole thing falls apart. We don't have a bond anymore. Right, so bonding and anti-bonding and talking about these orbitals is going to wind up being really important for how we predict some of these reactions. The other term that I want to bring up is this idea of a node. A node is any place where you have zero vibration. Have you done waves in physics yet? Okay.
Starting next week.
So remember, you didn't have me for quantum injection, huh? So you didn't see the electric guitar demo?
Oh.
So we do this. Basically, when you have a vibrating, I don't have my guitar with me. If you have a string that's vibrating, you get something similar. So if we have a string that's fixed on both sides and it's vibrating, we get a standing wave that looks like this. So just the string going back and forth, but the ends are fixed. So the ends don't vibrate. If we add a spot in the middle and exactly in between where nothing vibrates, we get a higher energy system.
Okay.
And so on a string instrument, this is called a harmonic. You put your finger exactly halfway between where the string starts and ends, and strike the string, you create a wave that's half the normal frequency.
Okay.
Because the wavelength is cut in half as well. So sorry, it's twice the normal frequency, half the wavelength. What that means is higher energy. Orbitals behave the same way. When you add a node in the middle, you create these shapes now have more curvature. And it turns out the amount of energy in different orbitals is directly proportional to how much curvature the shape itself has. So now we're getting into multivariable calculus in 3D, because you have to be able to, the surface area and curvature, I believe, is the first derivative of the surface area of a shape. But it's exactly what it sounds like. The more curved it is, has more curve to it than this does. Right? So it's higher energy. Orbitals do the same thing. When you add a node, it's going to be higher energy. In Gen Chem, we use this as an example of why electrons have to jump between energy levels. Because you can't just put one of these nodes anywhere. It has to be at an even fraction of the distance that the electron is confined in. So with sigma bonds, the difference between the bonding and the anti-bonding orbital is usually so big that we don't really care about it. You have to get into like gamma radiation before it actually starts making a difference. But there is every covalent bond has a specific frequency of light that corresponds to breaking that sigma bond. But with pi bonds, because pi bonds have less orbital overlap and are not as stable as the sigma bonds, oftentimes this gap is small enough we can actually get to it with the near UV light or visible light even. So it winds up showing up more often. And sorry, the other notation that I'll use is if this is a pi bond, the shorthand for an antibond, a pi antibonding orbital is pi star.
Okay.
So if you see that, that means antibonding. I told you we'd review quantum a whole bunch today.
I don't remember like learning it in the first, like I remember the concepts, but none of the like equations.
Yeah, that's fair. We're still not going to do the math. Because it turns out you can't actually solve these equations using math that we know.
Oh, okay.
Humanity as a whole cannot solve this. If you've heard of the three-body problem, it's a Netflix show, but it's actually a physics issue before that.
Okay.
Basically, if we have a nucleus and a single electron, we can directly calculate that energy because there's an attractive force between these, and we can just use our magnetic equation to say, okay, these are the charges, this is the average distance, this is the attractive force. As soon as you add a second electron, you can't do it because this electron is attracted to the nucleus but being repelled by that electron simultaneously, and you don't have math for that. We see the same thing with gravity in astrophysics. If we look at orbital dynamics, basically we can't calculate the gravitational pull on the moon from the Earth and the sun simultaneously. We basically just have to say, well, the Earth is closer than the sun, so we're only going to look at the Earth and the sun and ignore the sun.
Sure.
So it's called the three-body problem because two bodies, we can do it just fine. Three bodies, the math doesn't exist. So we actually can't solve these equations to get these energies by hand anyway. The best thing we can do is approximate it with computers, and it's still an approximation. It still doesn't get us a real answer.
Yeah.
All right, so when we have these bonding and anti-bonding orbitals, it turns out that if you have a conjugated system, it gets a little bit more complicated because now we don't just have two p orbitals overlapping, we have four p orbitals overlapping. So if we have 4 p orbitals, let me shrink that so it all fits on the screen.
And this is if we have,
If we have conjugated pi bonds, we have 4 p orbitals that we can align instead of just 2. Now there's more different ways we can combine them, and they're all gonna have their own energy. Because if we align them like this, so that all of them have blue up and red down, we get a system where it looks like one giant pi bond across the entire molecule.
Yeah.
If we add a single node to that, and we're always gonna add nodes symmetrically, so if we add a single node, it has to be right in the. If we add a single node, excuse me, we can still get 2 pi bonds, but they're not resonating. It doesn't look like they're resonating. And then if we add 2 nodes, it looks like we have 1 pi bond. And then we have a pi anti-bonding and a pi anti-bonding, so that looks like no resonance either. Then the highest possible energy is if it switches every single time. Red up, red down, red up, red down. Now we have no pi bonds. Because nothing's overlapping. So that's gonna be our highest energy. Basically, the more overlap you have, the more they're in phase, the lower energy it is. Right, and so if we're just drawing it as a schematic, instead of trying to show the shape of the molecule at the same time, it would look something like this. So, and the way that I do this by hand, that's faster than color coding it, is instead of using red and blue, I'll do shaded and unshaded.
Okay.
So if I was drawing this by hand, I draw 4 figure eights. Just like that. You two like to color code things, which is even better. You can color code them too. It's helpful. So it turns out most of the interesting chemistry happens at what we call the frontier orbitals, which I quite like the name of. The frontier orbitals. The frontier orbitals are the ones that are at the border. That's actually what frontier means. It means at the edge.
right,
So the frontier orbitals is the highest energy orbital that has electrons in it, and the lowest energy orbital that doesn't have electrons. Right, so we call that the highest occupied molecular orbital, or HOMO, and lowest unoccupied molecular orbital, LUMO. Right, so this, we get to another Nobel Prize. Kenichi Fukui was the first non-European, non-American to win a Nobel Prize. It was in 1981. So he won the Nobel Prize in 1981. This research that he did on this actually was done in the early 50s. So he actually had to wait 30 full years to get a Nobel Prize, which is much longer than the average. And it likely is because he's Japanese. And it's in the US and in Europe after World War II, there were a lot of people that held grudges against the Japanese for, well, all of World War II, basically.
yeah,
So he basically got kind of blacklisted until the point where they wanted to give 2 other Americans the Nobel Prize for the same research. They couldn't really leave him out at that point. They did their research about 10 years later, and expanded on what he started with, they couldn't really give them the Nobel Prize without including Fukui. Could be. I think they had to wait till enough of the people on the Nobel Prize committee that actually awards it didn't have, we're no longer racist. It's actually a really good Mad Men episode. I'm not a huge fan of Mad Men, but I think it did capture, they brought in, I think it was Honda that wanted to hire an ad agency that Don Draper worked for to advertise their new motorcycle or something like that. And half of the firm were veterans from World War II that served in the Pacific, and they were very, very racist and strongly against the idea of doing any business with the Japanese. So it's unsurprising that even the Nobel Prize Committee had a touch of that.
Yeah.
Because we don't think about it, but the scientists actually, they played a really big role in World War II. And Kenichi Fukui actually worked for the Japanese government or Japanese military on research for trying to make synthetic fuels because they were having trouble getting diesel fuel for their ships and their tanks and stuff. So he actually did aid the war effort on the side of Japan, but that's because he was Japanese. They was told to by the imperial government. They didn't really have a choice. So history, yay. So he came up with this term frontier orbitals. HOMO and LUMO are more commonly used these days. So if you say frontier orbitals, most everybody knows what you mean. Because typically, we're not going to have enough energy to promote electrons all the way from the most stable pi up to anything up here. There's too big of a gap here. But this is something we can do. And the more conjugated p orbitals you have, the more of these we have, the tighter this gap gets between the HOMO and the LUMO.
There's more p orbitals here?
Yes. Basically, we start getting more and more possible ways we can arrange these, but we still have to put the right number of electrons in. And so the difference in energy between the highest occupied orbital and the lowest unoccupied orbital winds up getting smaller and smaller. All right. Let's talk a little bit about how this affects the resonance in these orbitals affects the addition reaction. So remember I said isolated dienes, we just treat them like regular alkenes. If it's a conjugated diene, if we just try to add HBr to it, which is the very first addition reaction we ever did. So we're going away that for this one. If it was an isolated diene, and this carbon wasn't here, we would put the hydrogen on carbon 1, we put the bromine on carbon 2, and that's that. If it's a conjugated diene, we get some product that looks like that, but we get some products with a pi bond shifts.
Okay.
Because think about what the intermediate would look like after you add a proton with more substituted carbon here. Your intermediate is going to look like this, right?
Oh, so it's gonna shift them.
So you get a resonance structure that's going to look like this. So because we have two different places to put our positive charge, we have two different places for the bromide to attach. And we can choose which of these we make by changing the temperature. This is probably the classic example of thermodynamic versus kinetic control. So, as this reaction goes, they both make the same intermediate here. And this intermediate is the same because it's a resonance structure, so it's all simultaneous.
When the nucleophile attacks though, the 1,4 adduct has a higher barrier. So they call it the 1,4 adduct because you're adding your two atoms are being added on opposite ends, carbon 1 and carbon 4. Versus the 1,2 adduct would be 1 and 2. So the 1,4 adduct, the one that goes through this resonance structure, is the more stable product at the end, but it has the higher barrier. Basically, because this is less stable, because this gives us the primary carbocation. So this version of the resonance structure is not as stable, meaning it's going to have a higher barrier to get to this version. But once you do it at the end, we get the more stable product because we made the more substituted alkene. Remember Zaitse's rule? We're always going to preferentially form the more substituted alkene when we do elimination reactions, right? Because the more substituted alkenes are more stable. So this is our thermodynamic product, but the 1,2 adduct is our kinetic product. Because this version of the resonance structure is more favored.
Yeah.
And so, and what that looks like, we actually look at the numbers. At 0 Celsius, we get 70% of the 1,2 adducts. Because at 0 Celsius, not as many molecules have enough energy to take the red atom. At 40 Celsius, the number is about the opposite. 85% of it is going to make the 1,4 adducts. Because just that small difference in temperature is enough so that now enough of our molecules have enough energy to take the red atom. And if we made these more extreme, if we put this at -20, it's going to favor this even more strongly. And if we put it at even higher temperatures, we're going to reach a point where it doesn't make any difference, where it's actually the difference in energy here is going to have an equilibrium process away. But we can definitely get to probably close to 100% if we're willing to go slow by just making it cold. All right, so this is just if you want to do practice doing the mechanism, we already kind of drew it out. So we drew the two different resonance structures, right?
Yeah.
But just for practice, for this molecule, first step is hydrogen bond grabs hydrogen. Bromine keeps the electrons. So now we have a positive charge here. And our resonance structure is going to look like this. So if the bromide attaches to the first resonance structure, we're going to get one product. That's our 1,2 adduct. Adduct is kind of a funny word. It just means the result of an addition, but I don't think they wanted to use the math term for the result of an addition, but saying that that's the sum would be confusing. So they just made up a new word.
Okay.
The 1,4 adduct is what we're going to get here.
No, like, this needs more than we just did one.
So for this molecule.
Yeah.
We're actually gonna get more. More than that, because basically you pick a pi bond and you add hydrogen to the outside. Carbon, the less substituted carbon. Which puts a positive charge here that can resonate. We could have put it here, which would put a positive charge there, which would resonate over here.
Yeah.
So we would actually wind up with. The other products would look like. Bromine here. That would be the 1,4. Versus. This would be the 1,2. So we actually have 4 possible products here.
So like, what tells you that it's like 1, 2 versus 1?
Okay, so in order to get. Let's go with what we already have drawn out. Because I added, the first thing I did was I added hydrogen to one of the pi bonds, right? Right, the pi bond, I added the hydrogen here. So we're gonna call that carbon 1.
Okay.
So that means this is the 1, 2, because you put the bromine right next to where you put the hydrogen.
Yeah.
This would be the 1, 4, because where we added the hydrogen, the bromine are 4 carbons apart, or 3 carbons apart.
Okay.
Right, so then this one, we're gonna start adding hydrogen here, this is the 1, 2, this. So all we're really describing is where is the addition out relative to each other.
Yeah.
All right. Out of these. Can you erase the intermediates for a second? Which of these 4 is the thermodynamic product? Or if there are 2 that you think are equivalent.
Yeah. Obvious.
That one's got a tri-substituted alkene, right?
Yeah.
This also has a tri-substituted alkene.
Yeah.
So does this.
Yeah.
So all of those, we put those about the same. This 1, 2 is gonna be our least stable product. But it's gonna be the most quickly formed. It's the kinetic product, because if we look at the resonance structure that leads to each of these. We have that versus. That one. And over here, both of our resonance structures were secondary carbocations, right? So this is the only one that has a tertiary carbocation.
Yeah.
So this is our kinetic product. The other 3 are all thermodynamic products. They're all about the same level of stability. There might be some steroids that factor into it, because bromine's kind of big, and cyclohexane has those chair and both converters, things like that. But without getting into the nitty gritty, and those energy differences typically weren't that big anyway. All right, so to recap, kinetic product is the most stable resonance structure. Thermodynamic product is the most stable product, is the most stable alkene.
And if you get a very unsymmetrical molecule like this, sometimes you get more bonds.
It's like, I heard.
Yeah, I heard it too.
Well, lucky Carl.
Yeah.
So, you two girls watching It's a Wonderful Life
Yeah.
has that line with the little kid. And teacher says anytime a bell rings, the angel gets its wings. I feel like in chemistry it's gonna your glass breaking, somebody's learning something.
So true.
All right. In 15 minutes, I'm going to skip this one for now.
Okay.
These are the last 3 reactions we're going to cover this quarter.
They're all conjugated conjugated trianes. This is gonna be the one we spend the most, but they're all gonna use the same mechanism basically. So a cycloaddition breaks 2 pi bonds in order to make 2 sigma bonds. Because if you look at it beforehand, if you ignore these dotted lines, you've got 3 pi bonds to start with and 2 separate molecules. You're gonna break 2 pi bonds and you're gonna end with something that has 2 more sigma bonds. An electrocyclic reaction is kind of similar, except it's typically happening within the same molecule. And in an electrocyclic reaction, you lose 1 pi bond and gain 1 sigma. All right, and the last case is called sigmatropic rearrangement. Sigmatropic rearrangement doesn't have a net change in the number of bonds. Basically, if you move your pairs of electrons just right, you get the same number of pi bonds before and after, but just in different spots.
What's the little like orange one again? Yep.
Sigma
Orange? It looks like an orange. It's like a little.
with the stem.
Yeah.
I can see that. I would have gone with apple, but. All right, so, and you'll notice all of them have this same mechanism overall. You're moving 3 pairs of electrons. For cycloaddition, you're moving 3 pairs of pi electrons. For electrocyclic reaction, you're still moving 3 pairs of pi electrons. For sigmatropic, it's 2 pi electrons and 1 sigma bond moves. Again, we're going to keep coming back to this. Because if we think about the way this has to work, the pi orbitals have to be facing the right direction for this to happen.
Yeah.
Because your pi orbitals need to be oriented basically in the same direction as the sigma bonds you're going to be making.
So those frontier orbitals wind up becoming important when it comes to making sure that your electrons are in the right phase when they're overlapping, so that you get bonding orbitals, not non-bonding or anti-bonding orbitals. All right, so this is the one we're going to do in lab next week. The Diels-Alder reaction. This is the simplest cycloaddition, it's the most well-studied. You start with a conjugated diene and another alkene. When they react, it's just going to be 3 pairs of electrons moving in a circle. It's all the pi electrons moving. And the net result is we make a new ring structure. So a variation on this is what one sharpless is second Nobel Prize. The one that I worked on in grad school.
Yeah.
Looked really similar, except it was an azide reacting with an alkyne. And it does something similar. These electrons move over, these electrons move over, and these electrons move over. We get the same base, still a cycloaddition that involves 3 pairs of electrons moving. Oh, here's where it gets interesting. When we do this reaction with substituted alkene, so I guess the other term that we use is that this is the diene. We call the thing that's going to react with the dienophile. So just like with nucleophiles, electrophiles, it just means it's attracted to a diene. So we use a dienophile that is substituted. We see specific stereoisomers show up. So if we start with the substituents cis relative to each other, the ring structure we make still has them cis.
Okay.
If we start with them trans, our ring structure has them trans. So what would the transition state have to look like for this reaction to happen? So remember, we need these orbitals to be overlapping with each other. So if we have molecular models already drawn. If we have a diene,
Yeah.
and this is our dienophile. In order for it to attach, we add something else to this so we can see. This. So here's our dienophile, and it's our constituents are on the cis side relative to each other. In order for the pi orbitals here to overlap with the pi orbitals here, because that's where we're making our sigma bond, we're turning 2 pi bonds into sigma bonds, right? We basically can't just have this come in here randomly. It has to either come from below or above. Because that's how these pi orbitals and these pi orbitals can overlap with each other. Because remember, they're sticking above and below the carbons, not straight out. So it's never going to come straight in like this. It comes like this. And then when you make your new bonds, that's going to push these substituents towards being the same side. It's in here, we make our new bonds. We can kind of see it. It starts by making something that looks kind of like a boat complement, right?
Yeah.
Imagine that there's sigma bonds being formed here. And that means that this purple atom and this ethyl group are still going to wind up on the same side of the ring relative to each other, because it's not going to be able to come in twisted or like at this angle.
Yeah.
So because it has to approach from below or above, these are going to stay in the same configuration relative to each other. Let's do a practice. Most of our dienophiles
have other things that have pi bonds attached to them. Basically, the more electron withdrawing groups you have on your dienophile, the more it reacts.
So we'll see very commonly things that have other pi bonds that are conjugated with the dienophile.
So we make a cyclohexane. Yes, because your diene always has to have 4 carbons to be a conjugated diene. In our dienophile, it's 2 carbons. So when we make a ring out of that, we get 6 carbons. There can be other things hanging off of this as well, so your overall number of carbons might be larger. But the part that's actually doing the reacting is always going to be a hexagon.
Okay.
And so the way that this works is one of these pi bonds turns to a sigma bond, the other one moves over that way to make room for these electrons coming in. So pi electrons go that way, pi electrons go that way, pi electrons go this way. So what that means is we're left with 1 pi bond in between the 2 on our diene.
Okay.
So maybe I should color code this. So those are our 2 carbons that were part of the dienophile. And because we started with the cyanide groups trans relative to each other, here are our new bonds. This is one where having just a diene and something else with double bonds can be helpful because it lets you visually see, okay, I have to bring these up from the same side. If I have to bring them up from the same side, then I'm limited to where these are going to end up. All right, let me see what the next slide is, but we're probably done there.
The next one's just more practice. So we will stop there.
Do we have this process on the work?
On the quiz,
Yeah.
probably this part. We just added it, but I want you to get it tried the easy way before we introduce the tricky part, which is what happens when you catalyze it with light versus wind.
We do. That's the cool part.
It's like, but you're in.
You will be better prepared for life. You know about Lomo and the Limo.
I don't know. I don't think I'm really gonna be worried about this when I eventually become a vet.
No, but when somebody complains to you about the Diels-Alder reaction, say the Diels-Alder reaction's not that bad. I remember that. Let me go read my OChem textbook.
Yes. That's what we don't have done.
Absolutely not. That would be awful. Won't somebody think of those poor publishers?
Taking so much money all the time.